How does science see happiness? It's all in the mind, a suggestion that mental illnesses are more of a pushover than physical ones. Has long been a favorite way to shrink our troubles down to size. If there is any truth in this, one implication might be that happiness is all in the mind too. This begs an important question. Is there some province of the gray matter where we could bang a stake labeled happiness, some well-delineated region of the cerebral cortex, perhaps, that acts as the engine of our joys and delights? Given that the human brain has evolved in unplanned, bottom-up fashion from the less sophisticated precursors of fish, amphibians, reptiles, and rodents over many millions of years, the reality is unlikely to be so simple. If no one designed the brain to be happy from the top down, happiness must have evolved from the bottom up to serve some specific purpose. But is the happiness we struggle toward in our everyday lives the same thing as the happiness that occurs inside our brains? And does one necessarily create the other? Such questions have moved center stage for neuroscientists who are now probing the mechanisms by which our brains turn genetic predisposition, past experience, and everyday events into powerful emotions like anger and fear, depression and joy. Their quest, which uses science to probe the mental mysteries of emotion, is slowly revealing the secrets of the happy brain. Modularity of mind, a brief history. Evolution thrives on chance. Yet the brain, the most complex, and arguably the most important organ in the human body, is organized in anything but a haphazard fashion. Far from being a cluttered attic, jammed with random memories, and a lifetime of chaotic experience, the brain is a self-organizing, general-purpose information processor far more robust and adaptable than any computer. Scientists and laymen are equally fond of likening brains to computers, and vice versa, and the comparison has proved remarkably fruitful for the study of both kinds of thinking machine. A branch of psychology called cognitive science has made enormous leaps in helping us to understand the brain by viewing mental tasks as series of steps not unlike computer programs. Meanwhile, computer scientists have discovered they can set up and program machines as neural networks, highly interconnected computer systems that think in parallel, carrying out many operations simultaneously, much like the human brain is believed to do. The logical conclusion of this work is a gradual blurring of human minds and artificially intelligent machines, long forecast by computer scientists such as Ray Kurzweil. In December 2004, neuroscientists hinted at the shape of things to come when they wired a rat's brain to a computer and trained it like a neural network to fly a jet fighter. The idea that the brain is a modular machine whose components have fairly specialized roles is often portrayed as a modern discovery. It is modern brain imaging techniques, for example, that show different regions of the brain lighting up when people are asked to think, reason, or remember in different ways. Yet the modularity of mind is actually a much older idea. Splitting the brain. Think how the human brain has developed through millions of years of evolution, from fish and reptiles to rodents, apes, and humans. Now imagine an ancient brain, sitting on a table in front of you, making the same evolutionary journey in fast motion. You'd see it evolving upward and outward, starting from the brain stem, then adding structures like the cerebellum, then midbrain structures, and the limbic system, before the cortex grew on top, the whole brain surging triumphantly upwards and outwards. A bit like a slowly inflating balloon with all the gutsy attitude of a space rocket. Something similar happens in a developing fetus. At 14 weeks, only the brain stem, midbrain, and limbic areas have properly developed. The cortex, the seat of cognition, does not properly develop until around 6 months. Today's neuroscientists are making the same journey in reverse, as they try to understand the brain from the outside in. The starting point, the most obvious part of the brain, is the cerebral cortex, the convoluted sausage-like mass that sits on top. The cortex, and much of the brain beneath it, is split into two mirror images, the cerebral hemispheres, connected by the neural equivalent of a parallel printer cable called the corpus callosum. Each hemisphere of the cortex divides into 4 regions or lobes: the frontal, temporal; on the side, parietal; in the middle towards the back, and occipital; at the very back. Under the cortex is the limbic system, populated by intriguing-sounding organs that play a major role in emotional processing, and score highly in Scrabble: the amygdala, thalamus, hypothalamus, septum, and hippocampus. Under the limbic system lies the midbrain, the pons, and medulla, and the brainstem. At the top of the brainstem is the cerebellum, little brain, whose job is mainly to control movement and muscle operation. Arguably, calling this remarkable collection of control machinery, emotional apparatus, and seat of such higher functions as language, memory, and consciousness the brain, singular, is little more than a semantic convenience and no more helpful than referring to the rest of our flesh as the body. In other words, brain is a collective adjective like museum, or family that belies the richness of the things it contains. During the 20th century, neuroscientists made a great start splitting not just the gross structure of the brain but also cognition and emotion into their components. In the 21st century, splitting the brain and understanding exactly how the different components and circuits work together will doubtless be seen as a scientific achievement, as great as splitting the atom. Bumps on the skull. Like much of modern medicine, the idea that different parts of the brain do different jobs seems to have cropped up first in an Egyptian manuscript discovered by Edwin Smith in Luxor in 1862, itself generally believed to have been copied from a much older document that dates back to 3,000 years before Christus. The Edwin Smith Papyrus, as it has since been known, is generally regarded as the world's first scientific document, and contains 48 medical case studies, including this account of how brain damage can lead to specific disorders of bodily functions. If thou examinest a man having a smash of his skull, under the skin of his head, while there is nothing at all upon it, thou shouldst palpate his wound. Shouldst thou find that there is a swelling protruding on the outside of that smash, which is in his skull, while his eye is askew because of it, on the side of him having that injury which is in his skull, and he walks shuffling with his soul, on the side of him having the injury which is in his skull. Influential early thinkers like Aristotle, Galen, the father of Western medicine, and St. Augustine supported the idea that the brain's ventricles, large, open cavities inside the brain that are filled with cerebrospinal fluid, were the seat of higher mental functions such as thinking and reasoning. This view persisted, as medieval science was inclined to do, for many centuries. During the Renaissance, Leonardo da Vinci and Andreas Vesalius lifted the lid of the skull to make accurate anatomical sketches of what they found inside. Taking the human body apart and numbering the pieces, not unlike a medieval Haynes manual, Vesalius was illustrating parts of the brain and speculating they were dedicated to different mental functions, around 500 years before neuroscientists and brain scanners started doing much the same thing. The idea of the modular mind had its apotheosis with the phrenologists, a group of 19th century scientists, who believed the brain was divided into distinct regions, each one specialized in something like memory, language, benevolence, or wisdom, with the whole cerebral territory as neatly demarcated as a map of beef cuts hanging on the wall of a butcher's shop. The phrenologists' plans of the mind embodied much the same pioneer spirit as the conquest of the New World and the scramble for Africa. At a time when European explorers were conquering whole new continents, phrenologists were staking similar claims on the brain. For Guinea, the Congo, and Abyssinia, read amativeness, sublimity, and suavity. As modern neuroscientists happily concede, the basic principle of phrenology, what they term localization of function, was perfectly sound. It is certainly the case that different parts of the brain do different jobs, although there is little to suggest the mental territory divides up quite so cleanly, as the phrenologists insisted, or that abstract mental functions, like hope or parental love, can be meaningfully localized at all. Worse, the phrenologists took their idea to a logical conclusion that seems ridiculous to us now. Everyone's skull has lumps and bumps, for no particular reason, but the phrenologists believed the cranial landscape was shaped by the size of the brain areas inside it. So, if a person's combativeness area was overdeveloped, a large bump might appear just behind and above their ear. Feeling a person's head for lumps and bumps could, therefore, be used to diagnose all kinds of mental illnesses and physical ailments. Or so the phrenologists led themselves to believe. The inevitable rejection of this quackery, by critics such as Pierre Fleuron, 1794, 1867, eventually led to the demise of the whole notion of localization of brain function in favor of the idea that mental functions were distributed more evenly throughout the brain, an idea known as equipotentiality, because different parts of the brain play an equal part. Staking claims on the mental landscape. It has long been fashionable to deride the phrenologists, those 19th-century pseudoscientists who thought bumps on the skull signified a person's character, as quacks and charlatans. In retrospect, phrenologists were indisputably the pioneers of modern neuroscience. Phrenology, the only true science of mind, began when a Viennese doctor, named Franz Joseph Gall, 1758 to 1828, proposed that the brain really consisted of a number of quite separate faculties. Possibly regarding the brain as just another part of the body, Gall also proposed that the size of each mental faculty was a measure of how powerful it was, and that the brain, as a whole, took its overall shape from the combined shape of its faculties. It made perfect sense for Gall to take this idea one step further, and propose that the landscape of the skull was determined by the faculties inside it, so that bumps on the skull signified something important about the development of different parts of a person's brain underneath. With practical applications not unlike astrology and fortune-telling, phrenology was more than a theory. A phrenologist would run his fingers over a patient's head, or use tapes and calipers to make more detailed measurements. Using a phrenological mind map, a plan of the brain based on Gall's list of 27 faculties, he could then reveal a person's character, abilities, and suitability for particular occupations. An idea not unlike modern-day psychometric testing. According to science historian Dr. John Van Wyhe, compiler of a detailed website of phrenological reference material, during phrenology's first heyday in the 1820s, 1840s, many employers could demand a character reference from a local phrenologist to ensure that a prospective employee was honest and hardworking. Computers in the mind. Cognitive psychology relies on computer-inspired models to illuminate the brain, where behaviorists assumed the brain was a black box. And a Pandora's box at that. Cognitive psychologists have filled the dark space with flowchart-style squares, linked with arrows, and tried to see where it gets them. Mental functions, such as memory, thinking, and reasoning, and action, the cognitive control of our bodily movements, are understood in terms of sequential processes that happen with just as much as logic as computer programs, but also, given the complexity of the brain, somewhat more human fallibility. Ulrich Neisser famously caricatured this approach in his 1976 book Cognition and Reality. No one has ever gone so far as to suggest the brain actually is a computer. Cognitive psychology has always been a heuristic, a kind of what-if scientific metaphor, designed to help science move forward. But having established that something like human memory, to cite just one example, has a number of quite distinct components, separate short-term or working memory stores for the things we hear and see, the temptation, nevertheless, has been to try to find where those components are actually located in the brain. To ground the computer metaphor of cognitive psychology in real, living gray matter. By itself, cognitive psychology could never have achieved this. As the behaviorists realized decades before, there are any number of ways that the black box might be wired up to produce a particular response from a given stimulus. Cars are all designed to turn fuel into motion, but piston engines, diesel engines, rotary engines, and even electrically powered fuel cells all do that job in more or less different ways. How, then, to bridge the gap between theoretical models of how our minds work and the brains, once memorably described as being like two fistfuls of porridge, that actually do the job? The solution has come from the brain sciences, a closely linked ensemble of neurological disciplines that study different aspects of the brain's workings in somewhat different ways. Neuroanatomy, for example, focuses on the structure of the brain. It can be studied by dissecting the brains of animals, or people who have died, or by looking at brain scans of living people. Neurochemistry looks at the chemical messengers, neurotransmitters, that carry signals between brain cells, around fairly well-defined circuits. Think of a science, put the word neuro in front of it, and you just might find a new way of shedding light on the brain. One of the most illuminating of the neurological sciences, neuropsychology, studies patients unlucky enough to have suffered lesions, relatively localized brain damage caused by strokes, brain tumors, and head injuries, and tries to find out what kinds of things those people can no longer do. If they suffered lesions in a particular part of their brain, and can no longer recognize people's faces, for example, but they can still perceive and recognize other objects quite clearly, that suggests the damaged part of the brain might have something to do with face recognition. Since the mid-1980s, cognitive psychologists and neuropsychologists have worked together increasingly closely. Cognitive psychologists have refined their flowchart process models of things like memory and language processing, partly by taking account of neuropsychological case studies, our theories of the various different kinds of dyslexia, the inability to process written language in the normal way, owe much to research of this kind. Similarly, like pioneer zoologists seeking out the snark, neuropsychologists have actively tried to find patients with fairly specific loss, what they term selective impairment or deficits, of certain mental abilities, such as the components of memory. Thus, neuropsychologists confirm the long-supposed distinction between short-term and long-term memory by finding two quite different types of amnesic patient, some of whom could remember only very recent events for a short time, selective loss of long-term memory, while others could remember only events in the distant past, and had no ability to store recent events, selective loss of short-term memory. Inevitably, cognitive psychology and neuropsychology have converged in a field known as cognitive neuropsychology. It has taken cognitive neuropsychology and the other neurological sciences some time to arrive where the phrenologists started. The basic conclusion is much the same: the mind is modular, and different parts of the brain do indeed have specialized functions. Psychologists have long known, for example, that the left hemisphere of the brain has a greater role in processing language than the right hemisphere. They also know that visual perception happens in the visual cortex, part of the occipital lobe, a region about 2/3 of the way towards the back of each hemisphere. Some mental functions have been localized in the brain with very great accuracy. Face recognition, one of our most important survival skills, is now believed to take place a very specific part of the visual cortex. Cognitive science has often been described as a new science of the mind, but as Joseph Ledoux powerfully argues, no science of the mind could be complete without an understanding of emotions. Where, then, does emotion fit in? High on emotion? Psychologists have identified some of the pieces of cognition and worked out where in the brain's jigsaw puzzle they fit. But it's early days still, and popular perception of neuropsychology has long been wide of the mark. The concept of left brain, cold, rational, linguistic, and right brain, emotional, creative, visual, epitomized by a best-selling self-help art book whose title exhorts people to draw on the right side of your brain, is risibly simplistic. The brain may be divided into two hemispheres, presumably an evolutionary adaptation that increases our chances of survival after a head injury of some sort, but our minds are not so neatly parceled. Even the phrenologists would have drawn the line, metaphorically, this time, at the idea of a brain so cruelly bisected into rationality and creativity. It's one thing to try to localize a fairly well-defined cognitive function, such as face recognition, in the cerebral cortex. It's something else entirely to ask how the brain handles a much more general collection of cognitive behaviors that might loosely be described as creativity. And the situation is even more complex when we turn to emotions. Unlike higher mental processes such as consciousness, which many scientists consider we do not share with animals, emotions are much older. In evolutionary terms, forms of behavior that humans and other creatures do have in common. Think of angry snakes and worried sheep. Another complication is that we tend to understand emotions from a largely emotional perspective. Historically, poets, storytellers, musicians, and actors have done more to illuminate emotions than scientists. Shakespeare's portrayal of Lear's descent into madness, written in 1605, arguably remains a more relevant and insightful account of mental collapse than anything Freud wrote 300 years later. Science is still popularly perceived as cold, logical, rational, and antithetical to the emotions. Scientists have no feelings, therefore science can neither reflect the dazzling light of heaven nor the dark damnation of hell. Science and art pound different roads. Art's duty is to parade and provoke, while science strives to explore and explain. Science can be dramatic, though its job, unlike that of art, is not to dramatize. From a scientific perspective, talking about the emotions is about as helpful as talking about the gods or the muses. There is no logical reason to believe that one emotion has anything in common with any other emotion, in terms of how or where it arises in the brain. Why should we believe that the brain mechanisms of happiness have anything to do with those of anger or fear? Why should we even, necessarily, believe that the same mechanisms that underlie one emotion underlie the opposite emotion? It does not automatically follow that depression is a gear that throws the engine of happiness into reverse, although there is some evidence to suggest this. If we cannot even clearly define emotions, or spell out what differentiates one from another, can we hope to understand how emotions arise in the brain? Is it really possible to take a brain apart and point to parts that make us happy or sad? Perhaps surprisingly, the answer seems to be yes. The medical model of mental illness. Understanding how and where emotions are processed in the brain is a tougher problem than understanding cognitive functions like memory or language processing. As we have already considered, higher brain functions like memory, based on the logical processing of information, lend themselves to the computational approach of cognitive science. There is nothing to suggest that emotions can be tackled in quite the same way. Computers do not, yet, have emotions, while less highly evolved animals, which lack some of our own higher cognitive functions, may be no less emotional than we are. All this suggests cognitive science might not be quite so illuminating when it comes to the study of human emotion. As Joseph Ledoux argues, to call the study of cognition and emotion cognitive science is to do it a disservice. Long before the cognitive revolution transformed their way of thinking, psychologists tried to understand emotions using other theoretical frameworks, especially in people who merited treatment because their emotions were out of balance or control. All psychiatry is, in a sense, concerned with treating emotional problems of one kind or another. For much of the 20th century, psychiatry was dominated by psychoanalysis, though other theories eventually elbowed their way in too. Thus, depression, one of the most common mental illnesses, can certainly be described in psychoanalytic terms. Freud might conceivably have diagnosed a female patient with postnatal depression as having penis envy. Equally, depression can be understood with behavioral, or behaviorist, theories. Learned helplessness, an essentially behavioral theory proposed by Ivy League psychiatrist turned happiness guru Martin Seligman, suggests people, and animals, become depressed when they learn that, no matter what they do, they cannot make their lives any better, and give up trying as a result. There are chemical theories of depression as well. How else to explain the success of antidepressant drugs such as Valium and Prozac? Given the rise of cognitive science over the last 30 years or so, it should come as no surprise that there are also cognitive theories of depression and cognitive, or talking, treatments. According to these, people become depressed through a pattern of faulty thinking, arresting automatic thoughts, and replacing them with more rational ones is the basis of highly effective and empowering treatments for depression such as cognitive behavioral therapy, CBT. Just as the prevailing wind of psychology favors cognitive neuropsychology and the idea that mental functions can indeed be localized in different parts of the brain, so the medical model of mental illness has gradually come to dominate psychiatry at the expense of psychoanalysis. In the 1960s, it was plausible for such fashionable anti-psychiatrists as the American Thomas Sauce to claim mental illness was merely a myth. The belief in mental illness, as something other than man's trouble in getting along with his fellow man, is the proper heir to the belief in demonology and witchcraft. Mental illness thus exists or is real, in exactly the same sense in which witches existed or were real. In similar vein, R.D. Laing romanticized schizophrenia as a kind of crazy disaffection not dissimilar to the angst-ridden existential nausea of 1950s left-bank intellectuals, perhaps the only sane response an individual could show to an increasingly mad world. For Laing, schizophrenia could be an ingenious act. The schizophrenic is often playing at being psychotic. A good deal of schizophrenia is simply nonsense, red herring speech, prolonged filibustering to throw dangerous people off the scent, to create boredom and futility in others. The schizophrenic is often making a fool of himself and the doctor. He is playing at being mad to avoid at all costs the possibility of being held responsible. Today, schizophrenia is rightly regarded as a serious, psychotic illness, most likely caused by defective brain chemistry, an imbalance of the neurotransmitter dopamine, that must be swiftly corrected with drugs, malady, not poetry. Laing's ideas, however sympathetic and well-intentioned they may have seemed in the liberal 1960s, are now regarded as somewhere between an interesting intellectual sidetrack, at best, and dangerous medical malpractice, at worst. Other serious mental illnesses such as depression and bipolar disorder, manic depression, are usually best treated with a combination of psychotherapy and medication. Illnesses like this are called affective disorders because they involve a disruption of affect, a psychiatric term sometimes used interchangeably with mood, but usually involving fluctuations of mood that last only hours or days, not weeks or months. For much of the 20th century, psychiatry was about using elaborate, and sometimes arbitrarily compiled, catalogs of symptoms, such as the American Diagnostic and Statistical Manual, DSM, to establish a diagnosis and then selecting an appropriate treatment. The brain mechanisms underlying such things as depression and schizophrenia merited relatively little attention. The increasing effectiveness of drug treatments has brought not just a shift toward medical models of mental illness, but much more consideration of how and where emotions and emotional disorders actually happen in the brain. In other words, psychiatry is on a surer scientific footing than it has ever been. And, just like psychology, it is helping us finally to localize emotions in the brain. Putting emotions in their place. Understanding the neural basis of emotion essentially comes down to two things: breaking an emotional reaction, such as getting angry or feeling afraid, into a logical sequence of steps, and then understanding where and how each of those steps happens inside the brain. William James, 1842–1910, brother of the novelist Henry James, and one of the founding fathers of psychology at the turn of the 20th century, was also one of the first to attempt an explanation of this kind in 1884. James turned conventional, rational explanations of emotion on their head. He assumed we sense things, react to them instinctively, and then detect our own reactions, and it is the conscious interpretation of the reaction that amounts to the sense of an emotion. In other words, we see the mouse, jump on the chair, and feel scared because we have already reacted. In 1885, Danish physiologist Carl Lang, 1834–1900, independently proposed a virtually identical explanation, which is now generally referred to as the James-Lang theory. Later psychologists and physiologists, notably Walter Cannon, 1871–1945, in the 1920s, rejected the James-Lang theory because it could not explain why people felt subtly different emotions in different situations. There was another problem too. If laboratory animals have parts of their cerebral cortex destroyed, lesioned, they continue to show emotional responses, like rage, although they appear not to be consciously doing so, something Cannon famously termed sham rage. Cannon and his colleague Philip Bard systematically lesioned different parts of an animal's brain and observed how its emotional reactions changed. Through studies such as these, Cannon and Bard proposed that the hypothalamus, a peanut-sized structure buried deep beneath the front of the brain, or forebrain, lay at the heart of a complex emotional circuit. The idea that parts of the brain were specifically dedicated to handling emotion directly contradicted another of William James' suppositions. As far as James was concerned, there were no emotional circuits or components in the brain. Theories of the emotional brain crystallized between the 1930s and the 1950s, thanks to the work of two other pioneering neuroscientists. Working independently, American neuroanatomists James Pappas and Paul MacLean showed how various closely related components at the center of the brain linked together to form an elaborate emotional circuit. Apart from the hypothalamus, the other components include the amygdala, a larger structure located behind the hypothalamus, the hippocampus, a seahorse-shaped structure above, and slightly behind the amygdala, the thalamus itself, at the center of the forebrain, and the septum, next to the thalamus. They lie deep beneath the convoluted cerebral cortex that most of us tend to think of when we think of brains at all. Often known as the limbic region, these structures are believed to have evolved much earlier than the cortex, which is most extensively developed in humans, and believed to carry out the higher cortical functions, things like language processing and abstract reasoning, that define much of what it is to be human. Thanks to research like this, which had identified the likely components and circuits of emotion, a quite different approach to studying the neural basis of emotion became possible in the 1940s when Robert Heath, 1915 to 1999, a neuroscientist at Tulane University, used electrodes to stimulate specific regions of people's brains, and noted the emotional reactions that followed. Known as evoked potential studies, Heath's researches suggested that the so-called limbic system, the structures described above, were only part of a much more extensive collection of emotional circuitry that seemed to extend throughout the brain. Famously, Heath also discovered certain regions of the brain around the septum, in both animals and human patients, that came to be known as pleasure centers, places where electrical stimulation produced immediately pleasurable and deeply satisfying feelings. Heath's research took a new twist in 1954, with a now classic experiment by James Olds and Peter Milner. They implanted an electrode in the septum of a rat and wired it up to a switch that the rat could press all by itself. To their surprise, not only did the rat self-stimulate, pressing the switch to deliver a tiny burst of pleasurable electric current, but it did so thousands of times an hour. Olds and Milner ran a similar experiment with human patients, and showed, quite remarkably, that people were just as fond of intracranial self-stimulation, ICSS, as their whiskered counterparts. This groundbreaking research offered important and immediate benefits. Heath, for example, reduced pain in cancer patients, and seizures in epileptics using electrical stimulation of this kind. Others carried the idea much further than it was ready to be taken, claiming that the pleasure center theory should inform sweeping policies of social reform. British physiologist H. J. Campbell's 1973 book The Pleasure Areas was typical. Since then, the theory has fallen into disfavor with the apparent discovery that ICSS taps into brain circuits of craving and addiction, not those of reward. Ever since the James Lange theory, a central question about the neural basis of emotion has been how our fast, instinctive emotional reactions work with more measured, cognitive responses that typically follow later. In 1962, a pair of social psychologists at Columbia University, Stanley Schachter and Jerome Singer, added support to some of the ideas James and Lange had originally proposed. Schachter and Singer injected their subjects with adrenaline to increase their arousal, and put them in a room with stooges who were told to behave in a particular way, to behave angrily or euphorically, for example. Perhaps not surprisingly, the subjects who were not told about the purpose of their injection behaved in the same way as the people around them, Subjects who were informed about the purpose of the injection were unaffected by their surroundings. Although the results of this now classic experiment have been open to widely differing interpretations, they do add support to the idea of emotion as a nonspecific state of arousal whose meaning we derive from context. Psychologists and physiologists continue to probe the detailed circuitry of the emotional brain today. Circuitry is an appropriate word, and much more than a metaphor, because decades of research now seem to have established that emotions occur in the brain when neurotransmitter chemicals flow around fairly well-defined pathways. The New York neuroscientist Joseph Ledoux, for example, has devoted his career to exploring the neural circuitry that underlies our emotion of fear. A threat, like a snake in the woods, is perceived by the visual thalamus. That part of the thalamus devoted to processing sensory input from the eyes, which triggers a quick and dirty fear reaction in the amygdala, and a much slower, more measured response in the visual cortex that also, in time, refines the reaction in the amygdala. Hang on, that's a stick, not a snake. On this reading, fear is a fast-track, instinctive survival mechanism that makes all the difference between life and death. Ledoux makes it clear that we don't simply have one emotional brain. Emotions are indeed functions involved in survival. But since different emotions are involved with different survival functions, defending against danger, finding food, and mates, caring for offspring, and so on, each may well involve different brain systems that evolved for different reasons. As a result, there may not be one emotional system in the brain but many. Although there is no reason why parts of the brain, or circuits, that control anger or fear should have anything to do with other emotions, such as sadness, the sheer complexity of human emotions like love or jealousy may reflect the way different emotional circuits interlink or tap into common components. Other researchers have begun to explore these other emotions, happiness among them. Inside the happy brain. Just as cognitive neuropsychology has allowed neuroscientists to map regions of the brain devoted to obviously cognitive functions such as short-term memory and language processing, so a similar approach is successfully charting out the territory, both the components and the circuits that link them together, of our emotions. That territory encompasses parts of the subcortical old brain, in evolutionary terms, such as the amygdala and hippocampus, which are largely responsible for our immediate, instinctive reactions to people, events, and other things relevant to our survival. The territory also takes in the newer brain, the cortical areas built on top of those subcortical foundations, which have evolved more recently, and that distinguish humans from animals. How the cortical and subcortical areas work together is still not known. There are connections running in both directions between the emotional, subcortical brain and the rational cortex above. More connections run up from the subcortex to the cortex than in the opposite direction, which is probably why we so much at the mercy of our emotions, and why top-down, rational thought struggles to control such things as phobias, stress, and affective disorders like depression. Richard J. Davidson, director of the Laboratory for Affective Neuroscience at the University of Wisconsin-Madison, is one of the world's leading neuroscientists specializing in how the brain handles emotions. The name of his laboratory is something of a giveaway. Affective neuroscience is the term Davidson has coined for research into how and why the brain gives rise to affect or the mood states that we would call happiness, well-being, or sadness. Depression. Crucially, it's an interdisciplinary science that brings together physiologists, psychologists, cognitive scientists, and the social psychologists who have traditionally researched emotion, often from an anthropological perspective. It was Davidson who, ingeniously, wired up a meditating monk to a brain scanner, and demonstrated readings that were, in the words of Wired magazine, off the chart for happiness. Davidson sees his mission as the emotional equivalent of cognitive neuropsychology. First, to break emotion down into its components. Second, to see how different parts of the brain instantiate, include or give rise to, those emotional components. Meditating monks. The fastest way to find happiness in the human brain? The answer is almost facile. Make people happy and take a brain scan snapshot at the same time. Leading neuroscientist Richard Davidson has tried to do exactly this by making free brain scans of monks during meditation. In 2003, Davidson made world headlines when he tempted Mathieu Ricard, a monk with 30 years' experience of compassion meditation, a type of Buddhist contemplation, inside his brain scanner. During meditation, Ricard showed extremely high levels of activity in his left prefrontal cortex, an area of the brain closely correlated with happiness and positive affect. Ricard's activation levels were so high, in fact, that they surpassed those of over 150 subjects whom Davidson had previously tested in the same way. All this could be coincidence, or a freak finding. Maybe Ricard had high levels of frontal lobe activity before he became a monk, maybe it was this that drove him to pursue a life of monastic contemplation. Whether meditation leads to happiness or the other way around, the finding is certainly interesting, and seems to confirm what Buddhists have known for years, that meditation and physical and mental well-being are strongly connected. One of the key findings Davidson has to explain is the self-evident, but nevertheless crucially important observation that individuals react in different ways to different emotional stimuli. Some of us are easily upset, others have a remarkable degree of resilience that can see us through all manner of troubling events. Davidson argues that this is evidence for what psychologists call a diathesis, effectively, a double-edged sword of an explanation, the idea that our brain biology, genetically inherited or otherwise, gives us a predisposition to certain types of mood, or affective style, and environmental stresses interact with this to make each of us react with the unique emotions that we do. There are many ways of categorizing affective style. Some of us react swiftly, and recover quickly when challenging events try to trip us up. Some of us are more inclined to approach challenging stimuli, and tackle them head-on with a happier, more positive, and welcoming affective style that can help us achieve our goals. Others are more likely to withdraw, with a more negative affective style that reflects such emotions as fear and disgust. Withdrawal is the safer option, but it carries the risk of missed opportunities, helplessness, and depression. Approach and withdrawal, the yin and yang that distinguish one person's affective style from another's, play a fundamental role in happiness and well-being and seem to be controlled, instantiated, to use Davidson's word, in quite different parts of the brain. It's appropriate now to take a closer look at the structure of the brain and see if we can answer some of our earlier questions. Where are aspects of happiness or well-being actually taking place and, perhaps more to the point, how? What makes one person's emotional brain different from another's? And, other things being equal, is this what makes one person happier than another? The amygdala. Using brain scans, and a variety of other neuroscientific tools, researchers like Richard Davidson have identified key areas of the brain that seem to be implicated in controlling happiness. Not surprisingly, the limbic system, the brain's emotional heartland, is among them. The amygdala, we have one amygdala at the base of each hemisphere of our brains, plays a central role in processing information about outside events that have major emotional significance, especially those involving threats or dangers. In other words, the amygdala seems to be a kind of early warning system that alerts the cortex to looming threats, triggering at the same time fear or withdrawal reactions that can be toned down, if and when the cortex has had time to decide there is really nothing to be afraid of. Joseph Ledoux's book The Emotional Brain is a detailed exploration of this idea. One recent study found that patients who have bilateral amygdala damage, in other words, both amygdalas are impaired, rate strangers as more approachable and trustworthy than ordinary people would consider them, for example. A variety of other studies have noted that patients with depression seem to have enlarged amygdalas, or amygdalas with greater activation. One postmortem study of patients who committed suicide found they had significantly greater numbers of serotonin receptors in their amygdalas. But quite different studies have consistently reported that the amygdala is involved in laying down long-term memories, which begs a question: how are these findings related? Some researchers, including Richard Davidson, speculate that dysfunctional interactions between the amygdala and parts of the cortex may lead to a tendency to dwell on negative memories, and not see that the reality of the outside world doesn't necessarily reflect the darkness of the world within. There is also some evidence that the amygdalas in our two hemispheres work in oppositional ways. One recent study of gambling found the left amygdala showed greater activation when subjects were winning money, while the right amygdala was activated more when they lost money. The frontal cortex. Interestingly, the phrenologists located agreeableness and mirthfulness towards the front of the brain, and that's exactly where neuroscientists believe such qualities can be found today. The prefrontal cortex, PFC, as its name suggests, the front part of the cortex, also plays a major role in emotional processing. Different subregions within the PFC appear to be specialized for different tasks, although exactly what each region does is still not known. Key components include the orbital prefrontal cortex, OFC, and ventromedial prefrontal cortex, VFC, next to one another on the underside of the frontal cortex, and the dorsolateral prefrontal cortex, DFC, higher up and on the outside. According to psychologists Earl Miller and Jonathan Cohen, the prefrontal cortex manages goals and the way we achieve them. In other words, the PFC may act as a kind of working memory for effect. Davidson and his colleagues speculate that the PFC does this by balancing approach and withdrawal, inquiring. Left-sided regions of the PFC seem to be involved in making us approach things to satisfy our goals, and seem to be implicated in positive effect. Vigilant, right-sided regions make us withdraw, and are more implicated in negative effect. There is some speculation that the OFC and VFC are involved in the management of rewards and punishments, the left-sided OFC responding to rewards, and the right-sided OFC to punishments. The apparent specialization of different parts of the PFC is also borne out by neurological studies of patients with mental illness. Damage to the anterior front part of the prefrontal cortex of the left hemisphere is typically linked to depression. Damage to similar areas of the right hemisphere can prompt expansive, manic reactions. In other words, the implication is that the left hemisphere prefrontal cortex plays a key role in positive effect. Happy moods, while the right hemisphere prefrontal cortex seems to do the reverse. Davidson and his colleagues demonstrated this elegantly by showing happy or sad film clips to people known to have greater levels of either left-sided or right-sided brain activity in the prefrontal cortex. Those with more activity on the left side reacted more positively to the positive clips than those with more activity on the right side. Similarly, people with higher levels of right side activity to begin with reacted more negatively to the negative film clips. In other experiments, when normal subjects have been asked to make themselves feel sad, neuroscientists have noted a marked increase in blood flow, suggesting higher levels of activity in various parts of the frontal cortex. Richard Davidson sums up research into the role of the frontal cortex thus: we suggest that taking an active role in life and appropriately engaging sources of appetitive motivation, behaviors that are characteristic of left frontal individuals, may contribute to higher levels of well-being. The hippocampus and the anterior cingulate cortex, ACC. Best known for its role in helping to store long-term memories, the hippocampus, the seahorse-shaped structure adjoining the amygdala, also seems to play a key role in our emotional reactions. Davidson and his colleagues have suggested the hippocampus is a kind of emotional chaperone that helps to ensure our behavior is appropriate to its social context. This may explain why people with hippocampal damage often show emotions that are quite inappropriate at a particular time and place. Patients who suffer from post-traumatic stress disorder, PTSD, such as victims of war and violent attacks, can experience sudden extreme emotional reactions to quite innocuous stimuli. War veterans who burst into tears or dive behind the sofa when cars backfire are just one example. The anterior cingulate cortex, ACC, also seems to be involved in emotional processing, monitoring conflicts and triggering other brain circuits to carry out more detailed processing when they occur. Putting it all together, it's still too early to say exactly how these different components of the emotional brain work together to produce happiness, unhappiness, and other emotions. There are many connections running both ways between cortical areas, like the PFC, and subcortical areas, including the amygdala. It seems likely that the cortical and subcortical areas work in opposition, with the amygdala, for example, shooting first, triggering fast emotional reactions, and the cortex asking questions later, processing those emotional reactions further or trying to inhibit them some time afterward if they appear to be inappropriate. Richard Davidson believes affective style, how different people react to different emotionally laden stimuli, is also of prime importance in understanding why people are so different when it comes to emotions. Some people react quickly or slowly to emotional challenges, others react to a greater or lesser degree. Some recover more quickly. Davidson's research suggests the way people respond is caused by the relative contributions their left and right prefrontal cortices are making to the reaction. People with greater activity in the left frontal cortex tend to be happier and more optimistic, show greater positive effect, than people whose right frontal cortex is more active. Similarly, people with greater activity in their amygdala, and the right hemisphere amygdala in particular, are much more likely to be at risk from depression. This suggests some people are more at risk from environmental factors than others, especially because they seem to take more time to recover from negative stresses. Similar findings have also been confirmed in rhesus monkeys. According to Davidson, happier people can maintain a positive level of well-being because they can regulate negative emotions more effectively and reduce the time for which they last. Just how the cortical and subcortical areas work together remains one of the key mysteries of the emotional brain. But the division certainly fits our experience of sometimes being in two minds about things, having the sense of our head, our rational cortex, telling us one thing, and our heart, actually, our instinctive subcortex, telling us something else. It supports complex models of mental illnesses such as depression, which clearly have cognitive, behavioral, biological, and neurological components, and it explains why cognitive treatments can sometimes tackle these illnesses by tapping into the emotional circuitry at the cortical level as successfully as drugs, which alter our negative cognitions perhaps by influencing the same circuits at a more fundamental, biological level. Intriguing experiments. Some recent experiments looking into the neuroscience of happiness. Canadian neuroscientists Anne Blood and Robert Zador carried out PET scans of volunteers as they listened to highly pleasurable music that sent chills down their spine. The scans showed high levels of activation in regions of the brain linked with emotion, including the amygdala, orbitofrontal cortex, and ventromedial prefrontal cortex. Neuroscientist Dana Small and her colleagues persuaded volunteers to eat chocolate and used PET scans to see what happened to their brains. When the volunteers ate moderate, and therefore pleasurable, amounts of chocolate, their brains showed activity in one set of structures. When they carried on eating beyond satiety, so the chocolate became unpleasant and aversive, a different set of structures showed more activity. The researchers suggested there are two quite different circuits working in opposition, one responsible for reward and approach behaviors, and the other responsible for punishment and aversive behaviors. In November 2004, researchers at Bowling Green State University, Ohio, reported that people can feel joy or sorrow simply by imagining those emotions, and the types of movement that go with laughing or crying. 3 scans of these people showed that self-generated happiness or sadness stimulate the same parts of the brain as real emotions and music. Perhaps not surprisingly, according to study author Nakia Gordon, imagined laughter was effective at reducing sadness, and imagined crying reduced happiness. MS George and colleagues from the National Institute of Mental Health in Bethesda made their subjects happy or sad, either by showing them happy or sad faces or by asking them to recall happy or sad events from their lives, then took PET scans. They found this transient sadness activated a mixture of structures in the limbic system and the cortex, while transient happiness activated no particular region but led to a widespread reduction in cortical activity. They concluded, transient sadness and happiness affect different brain regions in divergent directions, and are not merely opposite activity in identical brain regions. R.D. Lane and colleagues took a group of 12 women, showed each of them film clips designed to provoke happiness, sadness, or disgust, and measured their brain activity with PET and other brain scans. All three types of film increased activity in the thalamus and medial prefrontal cortex. Sadness also increased activity in the anterior insula, while happiness raised activity in the ventral mesial frontal cortex. Looking to the future. In the end, perhaps there is nothing more depressing than the idea that our moods are hardwired in our brains, an essentially deterministic view of psychology that has our happiness or sadness contingent upon sudden power spikes in the emotional circuits. Such a view could be immensely liberating for some. People whose lives are crippled by severe mental illness are often relieved to find that what bothers them really is all in the mind, ultimately all in the body, and therefore susceptible, in time, to a medical cure. Richard Davidson and his colleagues have also considered how violence and impulsive aggression might be caused by disorders of emotional regulation, themselves caused by faults in the emotional circuits involving the PFC, amygdala, and other brain structures that regulate emotions. Imagine the extraordinary social repercussions of tracing violence to neural abnormalities and coming up with medical or behavioral treatments that put people in better control of their emotions and lives. Yet, despite the obvious benefits of understanding the neural basis of human behavior in cases like these, most of us are unlikely to find the idea of biologically determined moods so appealing. Quintessentially romantic, moods color our lives. Articulate psychiatric patients have often noted with some regret the passing of their demons when they are eventually cured. K. Redfield Jamieson, a psychiatrist who has charted her own lifelong battle with manic depression, makes a telling point when she talks of the bittersweet exchange of her intense, psychotic moods for a settled life on permanent medication. How can one ever bring back the long summer days of passion, the remembrance of lilacs, ecstasy and gin fizzes that spilled over a garden wall, and the peals of riotous laughter that lasted until the sun came down or the police arrived? Perhaps it's just as well that current neuroscientific wisdom does not support such a fatalistic view, or, at least, does not support it entirely. Richard Davidson champions the idea of a diathesis in which people's biological, or perhaps even genetic, predisposition makes them respond differently to different kinds of environmental challenge. Some people, in other words, are indeed dealt a better hand for happiness than others by having brains that are better wired for happiness to begin with. But that does not mean the rest are condemned to a lifetime of poor adaptivity and depression. Various different kinds of treatments for mental illness, from behavioral and cognitive treatments to drugs and electroconvulsive shock therapy, are effective to a greater or lesser degree in tackling illnesses such as depression. This suggests the mental circuitry of emotion is not immutable, it is plastic and its behavior can be changed by intervention. Although little research has been done into how, for example, cognitive therapy actually reduces the symptoms of depression, some studies have confirmed that it produces changes in brain activity comparable to those produced by medication. Using brain scans, Richard Davidson has also demonstrated that training in meditation techniques can have a dramatic effect not just on left-sided activity in the frontal cortex, strongly correlated with positive effect, but also on immunity to physical ailments. Remarkably, for example, it seems to increase influenza antibodies. The Dalai Lama, author of a book on the art of happiness, notes that neuroscience too has a crucial part to play in our understanding of well-being. The systematic training of the mind, the cultivation of happiness, the genuine inner transformation by deliberately selecting and focusing on positive mental states and challenging negative mental states, is possible because of the very structure and function of the brain. But the wiring in our brains is not static, not irrevocably fixed. Our brains are also adaptable. It's a suitably optimistic thought. Much like computers, our brains do what they do through a combination of hardware, neuroanatomical structures, and software, cognitions and chemicals. Even if the hardware constrains how we think and who we are, we can always change the software, reprogramming our minds, at least in theory, to make our lives happier and more fulfilled. Seeing inside the brain. Knowing what's going on inside someone's head has always been one of life's mysteries. The 19th century phrenologists thought bumps on the skull could solve that problem. Today, neuroscientists use a variety of different methods for seeing inside the brain. Lesion studies remain one of the most important methods of probing the brain's secrets. If humans or animals have suffered brain lesions, highly localized damage, and lose very specific mental functions as a result, neuroscientists can use that knowledge to build up a picture of which bits of the brain are responsible for which functions. Electroencephalography, EEG, has been used to measure brain activity in many experiments for the last few decades. Electrodes are fastened to the scalp to measure the voltage changes that are produced when the person is asked to carry out different tasks. CAT, computerized axial tomography, scans are essentially X-rays of the brain. CAT scanners build up pictures of the brain, using a narrow beam of X-rays, that makes an imaginary cut through the brain along a particular axis, and draws a cross-section on a computer screen. PET, positron emission tomography, scans trail the progress of radioactive glucose, as it courses through the brain. In more detail, the glucose releases, or emits, positrons, the antimatter, mirror image equivalents of electrons, which are rapidly annihilated when they meet electrons, giving off a burst of gamma radiation that is picked up by the scanner. 3. Functional magnetic resonance imaging. Scans measure changes in blood flow by sampling the electrical and magnetic activity of a living human or animal brain and display the results as a colorful image on a computer screen. Experiments ask their subjects to carry out particular tasks, or think certain thoughts, and then see which bits of the brain light up as a result. The bright areas on and free image show areas of the brain where blood flow and brain activity is higher than normal. Free scans can show the brain in much more detail than PET scans, and their resolution is constantly improving. And this is all about how does science see happiness. We hope you have found it interesting.